Jai Hind everyone, I am Dr. Ekta Pandey from the Department of Applied Science and Humanities, AKGEC, Engineering College. Today I am going to deliver a video lecture on a very particular topic, Charpit method, from Module 1, Partial Differential Equation from the course Mathematics 4 with subject code KAS 302 or 402. The content of today's video lectures are non-linear partial differential equation of the first order and their solution by using Charpit method. So before this lecture, I would like to suggest you that you must watch the video lecture on Lagrange's method. So let's start about Charpit method. First of all, let us recall what is partial differential equation. A differential equation containing partial derivative of a function of two or more independent variables is called partial differential equation. See, for example, for the function z is equal to fxy, you can see two equations, first and second. These two equations contain dependent variable z, independent variable x and y, and the derivative of partial derivative of z with respect to x and with respect to y. So these are partial differential equation. Beside these, P, Q, R, S, T are symbol used to denote partial derivative. See, P stand for del z del x, Q stand for del z del y, R stand for del 2z del x2, S stand for del 2z del xy, and T stand for del 2z del y2. So we can write our partial differential equation in terms of P, Q, R, S, T also. Now, today we will discuss about a very particular non-linear partial differential equation of first order. Very particular partial differential equation, and it is known as non-linear partial differential equation of first order. So let us see what is it. A partial differential equation is said to be non-linear of first order if the first condition is only first order derivative present in the equation. Second condition is the dependent variable and its partial derivative occur in degree higher than 1 or are multiplied together. We can understand this fact by some example. See, in first example, partial differential equation contain only first order partial derivative del z del x and del z del y, and dependent variable and its derivative are in product. So it is a non-linear partial differential equation of first order. See, in second example, again differential equation contain only first order derivative P and Q, but P occurs in degree 2. So it is again a non-linear partial differential equation of first order. In third example, also partial differential equation contain only first order derivative, but P and Q are present in product. So it is again a non-linear partial differential equation of first order. Besides this, we can assume all these equations as a relation between x, y, z, p and q, and we can write them in terms of a function of x, y, z, p, q is equal to 0. Means we can make its right hand side is equal to 0, then the relation in left hand side will be denoted by f. See, for example, first equation can be written as yp plus zq minus xy is equal to 0. Just make the right hand side is equal to 0. Then the expression in left hand side is denoted by f. Similarly, second equation can be written as p square minus y square q minus y square plus x square equal to 0. Third equation can be written as px plus qy minus pq is equal to 0. So we can always write such type of equation in the form f is equal to 0. And the general method to solve such a type of equation is a Charpit method. Today we will discuss about Charpit method. Now see, to solve solve the partial differential equation means we have to find a relation between dependent variable and dependent variable like z is equal to phi x y. We have to find this relation which will satisfy the given differential equation. So let's talk about the Charpit method. So let us start. What is Charpit method? First of all, let us given a partial differential equation which can be written in terms of f is equal to 0 as we discussed in the previous slide. This will be our equation number 1. Now we have to find its solution. So its solution is given by equation z is equal to phi x y. Okay. Now to find this solution, we are going to apply Charpit's method. So let us start this method, and according to this method, the first step is to find another relation between x, y, z, p and q. And this relation can be obtained by solving the Charpit auxiliary equation. These equations are given by equation number 3. See, you have no need to derive these equations, just note it down and learn them. Now, come to the second step. Here, we will find a solution of equation 3 which involve P or Q or both. See, this is a necessary condition to apply Charpit method. We have to find a solution which must contain P or Q or both. To find the solution, we are going to apply method of grouping, just like we do in Lagrange's method. What we have to do? We will select a pair of fraction from equation 3 which can be solved easily by direct integration, and the resultant integral should contain P or Q or both. Now come to the third step, but before this, the solution, if we can find such type of solution, then this solution is taken as another relation between x, y, z, p and q. So now we will have two relation between x, y, z, p and q. First one is this and second one will be this. So finding the solution of auxiliary equation, we will have another relation between x, y, z, p and q which is denoted by capital F. Now come to the step third. Here we will solve equation 1 and 2 for p and q. Like we do for simultaneous equation, we will solve equation 1 and 2 for p and q. By doing so, we will obtain the value of p and q in terms of x, y, z. X or y or z. So here we will obtain the value of p and q in terms of x, y, z. Now come to the next step. Now what we have to do? Just put p and q in the equation dz is equal to p dx plus q dy. What is this? See, this equation is nothing but the total derivative of the equation z is equal to phi x y. How? See, z depend on two variables x and y. So if we find the total derivative of z, then just apply the chain rule of partial derivative. Now differentiate first z with respect to x, then derivative of x. Differentiate z with respect to y, then derivative of y. See, it can be written as p dx plus q dy. So dz is equal to p dx plus q dy is nothing but the total derivative of z is equal to phi xy. Okay, now come to the next step. Here we have to find the solution of this equation dz is equal to p dx plus q dy just by direct integration. And if we can find this solution, then actually this solution is the complete solution of the given partial differential equation. So this is all about the Charpit method. Let us apply this method to some example. So I am going to discuss first example, and first example is find the complete integral of this equation by Charpit method. We have to solve this equation by Charpit method. Why? See, this equation contains only first order partial derivative P and Q, and P occur in degree 2. So obviously we have to solve it by Charpit method. To apply Charpit method, first step is to write the differential equation, partial differential equation in terms of f is equal to 0. Means just make the right hand side is equal to 0. And so this will be our first equation. Okay. Second step is to write Charpit auxiliary equation. Just write the Charpit auxiliary equation, and you can see here we can observe many partial derivative of f. We have to find all these partial derivative. We have to find partial derivative of f with respect to x, y, z, p and q. So let us find these partial derivative. So first of all, del f del x will be equal to 2x. Del f del y will be equal to minus 2y cube minus 2y. Del f del z will be 0. Del f del p will be equal to 2p. Del f del q will be equal to minus y square. Now what we have to do? Just put all these partial derivative in the auxiliary equation. We obtain dp upon del f del x is 2 upon x is equal to dq upon del f del y is minus 2y cube minus 2y. Del f del z is 0 is equal to dz minus p. Del f del p is 2p minus q, and del f del q is minus y square. Then is equal to dx del f del p is 2p is equal to dy del f del q is minus y square is equal to df upon 0. So this is our Charpit auxiliary equation. Now come to the third step. What we have to do? We have to find a solution of this auxiliary equation, and we have to select a pair of fraction which can be solved easily by direct integration, but the resultant integral must contain p or q or both. So let us find the simplest fraction. See, from first and fourth fraction, we have dp upon 2x is equal to dx upon minus 2p. See, if we simplify this, then we will obtain p dp is equal to x dx. Minus will be there. See, we can solve this equation by just direct integration. So what we have to do? Just integrate both sides. We can integrate it. Then we will obtain integration of p is p square upon 2. Integration of x is x square upon 2, and the constant of integration, I am taking it as c square upon 2 to maintain the symmetry of the relation. Now just simplify it, and we obtain p square is equal to c square minus x square. See, this relation contain p. So this relation can be taken as another relation between x, y, z, p and q. So we have two relation now between x, y, z, p and q. The first one is this and second one is this. Now what we have to do? The next step is to solve equation 1 and 2 for p and q. See, from equation 2 we can already find the value of p. P is equal to root of c square minus x square. P is equal to root of c square minus x square. So equation 2 directly provides us the value of p is equal to root c square minus x square. So what we have to do? Just put the value of p in equation 1 and solve the equation 1 for q. So let us find our next calculation. We have to find the value of q. So just put p square is equal to c square minus x square in 1. So let us find p square is equal to c square minus x square minus y square cube minus y square plus x square equal to 0. Simplify. this relation for q, we will obtain q is equal to c square minus y square upon y square, and it will be c square upon y square minus 1. So here it is the value of q. So we have obtained value of p and q in terms of x or y or z. Now next step, come to the next step. What we have to do? Just put value of p and q in equation. हमें कौन सी equation use करनी है? We have to put p and q in the equation dz is equal to p dx plus q dy. So put the value of p and q in this equation. P is equal to c square minus x square dx plus, and q is c square y square minus 1 dy. Now we have to solve this equation. We have to solve this equation by just direct integration. But see whether this equation is in direct integrable form or not. See, coefficient of dz is constant. Coefficient of dz is constant. It is 1. It is 1. Coefficient of dx is the function of x only. Coefficient of dy is the function of y only. So this equation is in direct integrable form. So we can find the solution by just direct integration. So next step is to apply integration. So integrate both sides, and we will obtain z is equal to integral of c square minus x square dx plus integral of c square upon y square minus 1 dy. Here we have to apply standard formulas of integration. Integral of c square minus x square is given by x upon 2 root c square minus x square plus c square upon 2 sine inverse x upon c plus integral of 1 upon y square is minus 1 upon y, and integral of 1 is y, and plus constant of integration. So here we obtain the solution of equation 3. We have obtained the solution of equation 3, but actually it is a complete solution of the given partial differential equation. The solution of 3 is a complete solution of the given partial differential equation. It is a complete solution of given partial differential equation, which was denoted by 1. So that's all about the example 1. Let us discuss some more example. See, in this example we have to solve the equation px plus qy is equal to pq. Here again you can see the equation contain only first order partial derivative p and q are present in product. So it is a non-linear partial differential equation of first order. Therefore we can solve it by Charpit method. So first step is to write the equation in the form f equal to 0, means just make the right hand side is equal to 0. So we obtain our first equation. Then second step is to write Charpit auxiliary equation and find all these derivative of f, partial derivative of f with respect to x, y, z, p and q. So if we obtain all these partial derivative, then we have to put the value of these partial derivative in the auxiliary equation, and we will obtain this equation. So come to the next point. If we obtain this auxiliary equation, then what we have to do? The next step is to find the solution of this auxiliary equation, and this solution must contain p or q or both. So here again we have to select a pair of fraction such that the resultant integral must contain p or q or both. So let us find the simplest fraction. See the first and second one. from first and second fraction, we have dp upon p is equal to dq upon q. See, we can solve this equation just by direct integration. So just integrate both sides, and integral of 1 upon p will be log p, integral of 1 upon q will be log q plus constant of integral. Constant of integral is taken as log c to maintain the symmetry of the relation. And now by property of log, we can write it as like p is equal to qc. So we have p is equal to qc, and this solution contains p and q both. So this solution can be taken as another relation between p, q, x, y, z. Okay, so now we have two relations, first and second, as a function of p, q, x, y, z. So what we have to do in next step, we will solve first and second for p and q. So let us find the value of p and q by solving equation number 1 and 2. What we have to do, from equation 2 we have p is equal to qc, just put p is equal to qc in equation 1 and just solve equation 1 for q. So let us do it. We have px plus qy minus pq is equal to 0. Here what we have to do, put p is equal to qc. So we will have qcx plus qy minus q square c is equal to 0. Now just simplify this equation for q. So we will have q square c is equal to qcx plus qy, and qc is equal to cx plus y. This implies q is equal to cx plus y upon c is equal to x plus y upon c. So here we have obtained value of q in terms of x and y. Q is equal to x plus y upon c. Next, since we have q is equal to x plus yc, therefore we can easily obtain the value of p, because p is equal to qc. This implies p is equal to, just put the value of q, and it will be cx plus y. So now we have value of p and q in terms of x, y or z. Now next step is to put p and q in equation. Equation is dz is equal to p dx plus q dy. We have to put value of p and q in this equation. So let us put, we will get dz is equal to p is cx plus y dx plus q is x plus y upon c dy. Now we have to solve this equation just by direct integration, but see whether this equation is in direct integrable form or not. See, coefficient of dz is constant, it can be solved by direct integration, but coefficient of dx is a function of x and y. Coefficient of dy is also a function of x and y. So it cannot be solved by direct integration. But one thing we can do, see, simplify it and write it like now. See what happened? This term is in direct integrable form, this term is in direct integrable form, and this term is also in direct integrable form. But here coefficient of dx is function of y, coefficient of dy is function of x. But if we make pair of these two terms, then this pair can be written as, we can write it like plus derivative of xy. See, by product rule, if we differentiate x into y, then we will obtain y dx plus x dy. So by product rule, we can write y dx plus x dy as derivative of xy. And now it is in direct integrable form. We can solve this term by just direct integration. Okay, now what we have to do? Just integrate both sides. We will obtain z is equal to integral of x is x square upon 2. Integral will be cancelled by derivative and we will obtain xy plus integral of y will be y square upon 2 plus constant of integration. This is the solution of our equation, of this equation, and we know that the solution of this equation is also a complete solution of the given partial differential equation. So it is a complete solution of the given partial differential equation. So this is all about the example 2. Let us discuss one more example. Example 3. Here again we have to solve a differential equation which is a non-linear partial differential equation of first order. See, it contains only first order partial derivative p and q are present in product. So it is again a non-linear partial differential equation of first order. Now what we have to do, first step is write the equation in terms f is equal to 0, means we have to make right hand side is equal to 0. This is our first equation. Next step is to find all partial derivative that will be used in Charpit auxiliary equation. So first of all write Charpit auxiliary equation and then find all these derivative. We have to find all these derivative and then put the value of all derivative in the differential equation, this auxiliary equation. Now next we will obtain, when we put all the values of partial derivative, then we will obtain this equation. And now we have to find the solution of this auxiliary equation, and the solution must contain p or q or both. So what we have to do, we have to select a pair of fraction which can be solved by direct integration, and its integral must contain p or q or both. So see, we have to find simplest fraction, and see here in the auxiliary equation we have dq upon 0. See, if we take this fraction with any other fraction, then by cross multiplication, just by cross multiplication, we will have dq is equal to 0. And see, this equation can be solved by simple direct integration. So just integrate both sides, we will obtain q is equal to a. Now see, this solution contains q, so it can be taken as another relation between x, y, z, p and q. So now we have two equations, equation 1 and 2. The solution of equation 1 and 2 will provide the value of p and q in terms of x, y, z. So what we have to do, solve equation 1 and 2 for p and q to find the value of p and q in terms of x, y, z. So let us see. From equation 2 we already have the value of q. What we have to do, just put the value of q in 1 and simplify this equation for p. We will obtain the value of p in terms of x, y, z. So these are very simple steps as we discussed in the last previous example. So just put the value of q is equal to a in equation 1 and simplify it for p. We will obtain the value of p. Now let us discuss the next step. What is the next step? We have obtained the value of q and p. Now we have to put p and q in the differential equation. Which differential equation? See, the differential equation is dz is equal to p dx plus q dy. We have to put the value of p and q in this equation. So put value of P and Q, then we will obtain this third equation. This is value of P and Q is equal to A. This is the value of Q. Now, we know that we have to find the solution of this equation just by direct integration. So, by direct integration, we can solve this equation, but first see whether this equation is in direct integrable form or not. See, coefficient of dz is constant, we can solve it by direct integration. Coefficient of dy is constant, we can solve it by direct integration. But here, coefficient of dx is a function of x, y, z. So, we cannot solve it by direct integration. So, what we have to do, see, if we can remove this factor, z minus ay, then the rest of the coefficient will be function of x only. Then it can be solved by direct integration. So, let us try to remove this factor z minus ay, and to remove this we have to divide the whole equation by this factor, then we will obtain I have divided the equation by z minus ay. Now, we will obtain 2x upon x square minus a dx plus a upon z minus ay dy. Now, see what happened. This term is in direct integrable form, but now coefficient of dz is function of z and y, coefficient of y is function of z and y. So, these two terms are not in direct integrable form. So, what we can do? We can make pairing. See, if we make pair of this term, derivative of dz and derivative of dy, then what can be done? See, we are going to make pair of these two terms. Now, just make more simplification. We can simplify left hand side by taking LCM, and we will get dz minus ay upon z minus ay is equal to 2x dx upon x square minus a. See what happened? Here, please read carefully this equation. You can observe that numerator is exact derivative of the denominator. See how? If we take t is equal to z minus ay, then its derivative will be dz minus a dy. So, by this calculation, you can observe that the numerator is exact derivative of denominator. So, it can be now solved by direct integration by this substitution. See, in right hand side also, if we take u is equal to x square minus a, then its derivative will be 2x dx. Now, we can easily solve the right hand side equation by this substitution. So, see the effect of the substitution. We can write this equation as dt upon t is equal to du upon u. Now, you can see by all these calculations, what happened? We can solve the equation just by direct integration. So, just integrate both sides. What will we get? Integration of 1 upon t will be log t is equal to log u, and constant of integration log b. By property of log, we have t is equal to bu. Just put the value of t and u. We have z minus ay is equal to b x square minus a, and z is equal to ay plus b x square minus a. So, this is the solution of equation 3, and also this is a complete solution of the given partial differential equation. So this is all about this example. Now you can now try this method to solve this equation p square plus q square into y is equal to qz. I hope you can do this example by yourself. So that's all about Charpit method. Thank you very much.